All right, so we're going to finish up our discussion of nuclear chemistry today. If you remember last time, we talked about all these different types of nuclear reactions. We had our alpha decay, our beta decay, gamma ray emission, our positron emission, and our electron capture. And these were all types of nuclear reactions that these radioactive elements will undergo, right? These unstable nuclei that are going to end up kind of falling apart in one way or the other, or changing in one way or the other, all right? So it turns out that all these radioactive processes happen with this characteristic half-life. And so that's where we're going to start our discussion here with half-lives of these nuclear decays. All right, so all of these unstable nuclides will undergo their nuclear reactions with first-order kinetics. All right, so any one of our reactions, if we know our particular nuclide, uranium-238, for example, was one that we looked at last class. It has this characteristic decay, which is always going to be first-order kinetics, right? All of these unstable nuclei will undergo their reactions with first-order kinetics. All right, so let's remind ourselves what it meant to be first-order. All right, first of all, we had our rate law. That told us that the rate was equal to some rate constant K times the concentration of that nuclide. We're going to use uranium-238 as an example here, to the power of 1. All right, that's what it meant to be first order, was it had this order of 1 in its rate law. All right, so first, what's actually going to be more important is this other set of equations that we talked about, are integrated rate laws. That also depended on the order of our reaction. And we found that the concentration of A at a given point in time was equal to the concentration originally times e to the negative kt. All right, so all of this should look familiar from, well, I mean, come on, it's been a while now. This is the very beginning of the semester when we talked about kinetics. But just to remind ourselves, we talked about these different orders. Remember, chemical reactions, they can happen with various orders. A lot of them are second order because they depend on two reactants colliding into one another. When we're talking about these unstable nuclei, they just kind of fall apart spontaneously. And they do so with first order kinetics. So they have this rate law here, or again, what we're going to be more focused on, this integrated rate law. All right, so our radioactive decay kinetics. The only thing is, with regard to these nuclei, we don't really care about, but rather talking about them in terms of concentration doesn't make a lot of sense. They're not dissolved in a solution. They're not in the gas phase. They're solids almost exclusively. So instead, we're going to use this exact same equation here, but we're going to drop the brackets, all right? Because we're not talking about concentration anymore. We're going to use this form N of T equals N naught E to the negative kt. All right, and N can be in grams or moles. Either one would work. So if we knew that we had 10 moles originally, we could use this equation here to figure out how much we're going to have after a given time. If we knew that we had 10 grams, we could use this exact same equation. Our units would change, but N can be in either grams or moles. And so our rate constant K we use to characterize the rate of these different reactions. In nuclear reactions, they don't use the rate constant K. They use instead the half-life. All right, and we learned, and I know this was everybody's favorite part of the kinetics chapter, was learning how to derive these half-life expressions given our integrated rate laws. Remember, we would just set n of t equals to n naught over 2, and we would solve for t to get this formula, which in the case of a first order reaction was that half-life equals the negative natural log of 1/2 divided by that rate constant K. All right, well, so again, since they don't really use this rate constant K in when they talk about nuclear reactions, they instead use this half-life here. What we're going to do is we're going to combine these two equations. What we're going to do is solve that T1/2 equation for K, and then plug that in to our integrated rate law. All right, so I want everybody to take this half-life expression here, but rearrange it to solve for K. Right? Currently, we have it solved for T1/2. We're going to solve for K and then plug it in up here to our integrated rate law. All right, I'm trying to get K all by itself. It's stuck on the bottom over there. It's in the denominator, so I'm going to multiply both sides by K and divide both sides by that T1/2. So what we're left with is K equals the negative natural log of 1/2 over that half-life. All right, so that's step one. Now we're going to turn around and plug it into this equation here. We solve for K, so we're going to substitute here for K. So then we get this new equation, e to the negative natural log of 1/2, so that's just positive natural log of 1/2 divided by our half-life times time. All right, so all I did was plug this in right here for K. Cool. All right, so now we're going to simplify this thing a little bit, and we're going to use this algebraic identity. We've used one similar to before, that if we have something like e raised to the a plus b, that's e to the a times e to the b. All right, but what if we have e to the a times b? That's e to the a what? Raised to the power of b. Awesome. So let's take this expression here and rearrange it. Let me condense things a little bit. Cool. So we have nt equals n naught e to the natural log of 1/2 all raised to the power of T over T1/2. All right, and then what's e to the natural log of 1/2? Just 1/2, right? So that's how we arrive at this equation here. N naught equals 1/2 raised to the power of T over that half-life. All right, and so this is what we're going to be using for our nuclear chemistry here. All right, just so we can label our variables here so we're super clear about what's going on. This is the amount of nuclide after time t has passed. All right, we're talking about a radioactive decay here, so that means that we're going to start out with some initial amount. That's what our N naught is. And we want to know how much there is after a certain amount of time. That half-life, that T1/2 is again our half-life. And this is something that's characteristic of these different nuclides. So for example, uranium-238 has a different half-life than plutonium-242, has a different half-life than some other radioactive element that you can think of. Each one of them has a characteristic half-life, and then the kinetics are governed by this equation here. All right, and then so the T then is just the amount of time elapsed. Whoops. You could have used the other form with the E in there. You didn't have to go through all of this algebra to simplify here. All right, the reason that we like this equation is because T divided by T1/2, this is simply the number of half-lives that have elapsed. Right, so if your half-life is 2 minutes and it's been 4 minutes, how many half-lives have elapsed? 4 divided by 2, or 2 half-lives, right? So that's how that's kind of like why we like this expression here. It makes sense within the context of these half-lives. Cool. All right, so we're going to use this equation, but we're going to use it in 2 very specific contexts in which they use. All right, the first one we're going to talk about is carbon-14 radio dating. All right, this is when we use the amount of carbon-14 in a sample to determine how old it is. All right, first we're going to talk about why this works, and then we'll do the math behind it. All right, so there are a few important points here. As you may have guessed, carbon-14 is an unstable isotope of carbon. All right, so we're going to be using these nuclear reactions here to better understand what's happening. Carbon-14 is one of those radioactive isotopes of carbon. All right. So how can we use carbon-14 to figure out how old something is? All right. Importantly, the amount of carbon-14 in a living organism remains constant. All right, so first of all, we're not talking about using this to figure out how old you or I am. We're talking about using this to figure out how old some ancient creature is that we just dug up out of the ground, something that's been long dead. How long has it been since that organism was walking this earth? You can use it on plants, you can use it on animals, but it has to be something that was once living. It doesn't work for like rocks and stuff like that, all right? But yes, the key here is that when that thing is alive, it had this constant amount of carbon-14. So how does that work? I just told you that carbon-14 is unstable, and then I told you that the amount of carbon-14 in you and me is constant. So how does that work? It should be changing if it's unstable, right? Cool. So this is a little bit, we're going to have some backstory here, all right, to sort of lay this out. So first of all, where does that carbon-14 come from? Because if it's unstable, then it sort of reasons that all of it here on Earth should eventually not be here anymore, right? So how is it even here in the first place? Cool. So first, that carbon-14 is formed in the upper atmosphere. All right, as CO2. Okay, so first of all, where is carbon in our atmosphere? When we talk about carbon in our atmosphere, we're talking about carbon dioxide. All right, so we have C14, or rather we have carbon in carbon dioxide being formed that's labeled with this isotope here. All right, and how does that happen? Through this process called neutron capture. All right, this isn't a decay process that we were talking about before. This is something that's powered by the energy of the sun. The sun's kind of raining down these particles in our upper atmosphere. That's what our atmosphere is protecting us from, is all this crap that the sun is spewing at us. Well, in the upper atmosphere, it's not as protected. So turns out that the nitrogen in that upper atmosphere gets bombarded with these neutrons and forms carbon-14. All right, let's stop here and practice balancing our nuclear equations here. If carbon-14 forms, what is my other product that has to be formed in this reaction based on these balancing rules that we learned last class? So not quite, because the positron would have a mass number of 0. And remember, that's the goal here, is to make sure that our sum of our mass numbers are the same and the sum of our atomic numbers are the same. So we're going to need, what's my atomic number going to be of my product? 1, so that they both add up to 7. What's the mass number going to be of my product? 1, so this would be a hydrogen atom that's formed. So in the upper atmosphere, we got a bunch of nitrogen in our atmosphere. The sun is chucking neutrons at it. Every once in a while, one of those nitrogens gets converted to a carbon-14 nuclide, which then gets incorporated into our atmosphere as carbon dioxide. So then how does it get in our body? Exactly, right? So this carbon dioxide, we would say, is exchanged with living organisms. All right, well then how does that work? Well, let's think. How would it get inside of a plant? Photosynthesis. All right, and now we have carbon-14 in these plants here, but then how do they get inside animals? Animals eat plants. Even if we eat other animals, those animals used to eat plants, right? The base of our food chain always starts with plant life. And so absolutely, through our food chain. All right. And then it remains constant over time in our bodies. We're not constantly just accumulating carbon-14 because we also release carbon in the form of respiration and less gloriously excretion. Plants also kind of respire, but they tend to just grow and grow and grow. They also shed their leaves. That would be another way of getting rid. All right, but the bottom line here is that the amount of carbon-14 remains constant. All right, and that is until you die. At which case you are no longer eating, plants are no longer photosynthesizing, so we're no longer taking up any new carbon-14 at that point. All right, so that organism dies. No more C14 uptake. So then what happens to all that carbon-14 that we've acquired? It decays, right? And importantly, it decays with this characteristic rate. And so that's how we can use the amount of carbon-14 in a once living organism to figure out how old it is. Because all carbon-14s decay with a certain rate. And so by knowing that rate, which we do, we can figure out its age. Carbon-14 begins to decay with its characteristic rate. Cool. All right. So let's ask ourselves here. We're going to try to put what we've learned into practice here. First of all, let's try to figure out what type of those radioactive reactions, radioactivity, does that carbon-14 have? One thing that I guess I want to put out here, I'm being very lazy with my nuclear symbols by not putting my atomic number here. That's because we know that carbon is atomic number 6. If we were to put this in a balanced chemical equation, then we want that number there to balance it. But this is kind of just fine when we're talking about our specific nuclide. All right, so let's go to our periodic table here. Ignore this electronegativity stuff. You know all about that. All right, and you're going to write me the balanced nuclear equation here that this carbon-14 nuclide is going to undergo. All right, remember the first step is we got to figure out which category does it belong to. Does it have too many neutrons, too few neutrons, or is it just too dang big? And from there, we can figure out the type of nuclear reaction that it's going to undergo. right, so what do we think? Too many neutrons or too few neutrons? Too many. How do we know? No. So yeah, what we want to do is we want to look at our periodic table and note that since these are all of our stable carbons, they all tend to have a mass number around 12, right? In fact, you didn't have to know this off the top of your head, but 99% of carbon is carbon 12. That's why its atomic number is so close to 12. And then there's about 1% carbon 13, and only the teeny tiniest trace amounts are actually these carbon 14s, because this thing has too many neutrons.
So the mass on the periodic table only counts stable isotopes of the thing?
Yeah, so if you notice, everything unstable here has a mass in brackets, and some of them don't, like uranium, and that's just because its half-life is like ridiculously long. We'll talk about that in a bit here, but these are just, even though they do fall apart on a time scale of billions of years or something. So that's why we can kind of get a bit more accurate picture of their mass. So if it's too many neutrons, that implies beta decay. Right? So that means that it necessarily produces a beta particle. A beta particle is just an electron. And then you're going to balance this nuclear equation for me. Remember, if this is 6, that means that this has to add up to 6. So what's my other number going to be? 7. 14. So we remade our nitrogen 14. Cool. All right, and that's what your homework assignment for this Friday will have you practicing here, is predicting these nuclear reactions. But yes, in this case here, don't worry about all that. Where are we at? We have too many neutrons. So beta decay. Okay, and in fact, this beta decay reaction, again, has this characteristic half-life. They all do. All right, and the magic number here for this beta decay is it has a half-life of 5,715 years. The half-life? Is the half-life of the decay of this carbon-14. So if you had a beaker of carbon-14, after 5,715 years, you'd only have half as much left, right? Half of it would decay in that amount of time. Cool. All right, so let's do a practice problem using our kinetics equation now. Let's say we have a sample of bone. And it contains 25% of its original mass of carbon-14. We want to know how old is the bone. All right, well, let's look at our equation again. And looking carefully at this equation, what is it that I'm solving for here? For t. How old is the bone? So I need a time frame, right? So absolutely, I'm solving for how much time has elapsed since that creature has perished, right? This is what we're going to be solving for. So now let's fill in our other variables here. I gave you the half-life. Again, the half-life's not going to change just because it's in a bone or a piece of paper. It's characteristic to that nuclide. Carbon-14 always has the same half-life. This is a constant. It's just a number, 1/2. All right, so then how am I going to figure out how much my n sub t and my n naught here? All right, so again, n sub t is the amount that remains. And my n naught is my amount that's initial. So how much remains after whatever amount of time that we're trying to figure out has passed? 25%. Which means how much did I have originally? 100%. All right, so then we just need to take this equation, we need to rearrange it, and we need to solve for that t. Now, it's going to be kind of a pain in the butt. It's stuck up here in this exponent, but we've dealt with that several times throughout this course. How do we pull something down from an exponent? Logarithms, natural log, you could use either one here, but that's exactly what we're going to need to use. All right, so let's rearrange this equation here. Divide both sides by 100. Okay. Again, in order to pull this out of that exponent position, I'm going to take the natural log, and I can do whatever I want as long as I do it to both sides. Right? And remember, the point being is that now that gets to be pulled out front here. That becomes t divided by t1/2 times the natural log of 1/2. All right, so rearranging this equation here, we get the natural log of 25 over 100 divided by the natural log of 1/2 times that characteristic half-life of 5,715 years. I'm going to plug that in here. I punch that into my calculator. I get 11,430. And what are my units here? Years, right? So your units are always going to match that of your half-life. All right, so whatever animal that bone belonged to was alive 11,430 years ago, based on the amount of carbon-14 that still remained in that bone fragment. There's kind of another easier way to do this, just given how nice and pretty and round this number is, 25%. Okay, so let's think here. If we had 100%, how much would be remaining after one of those half-lives have elapsed? 50%. And then how much is going to remain after another half-life has elapsed? 25. So half of that value. It just keeps decreasing by half each half-life. And so indeed, that 11,430 is just 2 half-lives, 2 times that 5,715. Importantly, this method, though, the long way will work regardless of what your percentage is. What's up?
I was just going to ask, for the 25 over 100, will it mess up if we bring that down to 1/4?
No, it would not. Nope. You could put in 0.25, that'd be perfectly fine. Yep. All right, one more thing that we're going to throw on here, just as a addition to our notes. They have this limit that they use after about 50,000. I've seen 60,000 as well in certain sources, but this is what our book says. After about 50,000 years, this technique doesn't work very well. You can use your equation to convince yourself that that means only 0.2% of the carbon-14 is left, and you just can't really measure it after a certain point. It's already present in a super tiny amount. So at some point, your detection limit kind of limits you on how old you can date stuff. So this is good for organisms, and again, this is a key thing. This works for once living samples at about a 50,000 year limit. But this is how we can figure out how old something is. They found some texts way back when that they thought pertained to stuff that was around, the type of Christianity forming, these Dead Sea Scrolls. And how did they figure out the date of that? Well, that stuff was written on what was once a living organism. It was written on papyrus. So they could then use this carbon-14 dating to figure out just how old that document is, right? So it works on anything that was once living. Cool. All right. So the other one that the other specific context that we're going to be using these nuclear decay equations for, our rates for, is what's called uranium-lead dating. All right, this is when we measure the amount of uranium-238 and lead-206 in a mineral to determine its age. All right, so how does this work? Well, many minerals take up heavy elements. Like that uranium-238. When they form. All right, a classic example that they like to use, and it's because it works particularly well, is what are called zircons, I think. That's how you pronounce it. These work specifically well because they incorporate uranium and not lead when they form. They're also super old. These are thought to have formed in kind of the very beginnings of the formation of Earth. There are a few others that this works for as well, but this is kind of like the crown jewel of where it works the best. All right, and then again, how this works is that uranium-238 is unstable. In this case, that uranium-238 falls into that category of just being too dang big. So it will undergo alpha decay as well as beta decay. Now, it doesn't just undergo that once. That would lead us to thorium. But instead, and this is just fun fact here, it undergoes several alpha and beta decays until it reaches a stable nuclei. So this is a particular path that it undergoes. One alpha, then a beta, then alpha, 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 beta, beta, alpha, beta, beta, alpha, until finally arriving at this stable isotope, lead-206.
Is it always that route, or does it sometimes take another?
I think this is pretty much the predominant route. I'm not saying that there isn't like a small amount that will follow something else, but this is kind of uranium-238 is fairly well studied compared to a lot of the other nuclear decays. And yes, this is definitely a preferred path, let's say. I will say I've seen other ones where like there's little side paths somewhere, but this is kind of the main one here. All right, so we're not going to write our full balanced nuclear equation with all those millions of steps. We're just going to note that it will continue to alpha and beta decay until it arrives at lead-206. And lead-206 is stable, so it's going to stop there. And so you're going to have your uranium-238 decaying and your lead-206 accumulating. And again, just like all nuclear equations, this happens with this characteristic half-life. Whoops, not N. But this one occurs on a little bit of a longer scale than our carbon-14 decay. This one occurs on a time scale of 4.47 billion years. All right, so again, let's use this to date a particular mineral here. Let's ask, how old is a sample of that zircon? That contains 0.36 moles of uranium-238 and 0.15 moles of that lead-206. All right, well, let's go back to our equation here. All right, we know our half-life of our material here. What is it that we're trying to solve for if we're figuring out how old something is? T. So we need to figure out how much remains. We got to get this down to one variable, right? So we got to figure out how much remains and our initial amount. All right, and importantly, this T1 half here is telling me about the decay of which one of these two nuclei? The uranium, right? So this is what's decaying with that characteristic half-life of 4.47 billion years. So then how much of that uranium-238 remains after this time has elapsed? Yeah, the amount that we measured, right? We went up to this rock, we cracked it open, we figured out that it is 0.36 moles of uranium. Well, it didn't just form, that's how much has remained after a certain amount of time. But now we got to figure out the initial amount of uranium that was in there. Cool, and how'd you get that?
I added the 36 we currently have and the 15 that we used to have it when we were.
Exactly, right? So this 0.15 moles of lead, where did it come from? Well, it used to all be uranium-238, right? So initially, all this 0.15 moles was uranium-238. So we just need to add these together, the 0.36 that we have currently plus that 0.15. Now, importantly, this only works in moles. All right, sometimes we can use grams in N as well, but if we're going to add these two things up, we can't add masses and have them be preserved because the mass of uranium-238 and the mass of lead-206 are not the same. We have to convert to moles first. All right, but then we have our T over T1/2. And again, we're going to have to solve for that T. So given what we did before, I want everybody to take a second and see if they can't tell me how old this mineral is here. All right, so again, I kind of arrive at the same place here. This is the natural log of n of t divided by n naught, my 0.36 divided by the sum of 0.36 plus 0.15, divided by the natural log of 1/2, times that half-life. Now, you may have converted that half-life into years by multiplying it by 10 to the 9. I'm just going to keep this as 4.47 and keep my units as billions of years. Then when I do my math here, I punch this into my calculator. I'm going to just say 3 sig figs here, 2.25. Then what would my units be? Billion years. All right, so how old is that mineral? It is 2.25 billion years old, based on the ratio of uranium and lead that is contained in that mineral. Cool. All right, so we have these half-lives, this fact that all of our nuclides, they decay with this very specific first-order kinetics, And we characterize that decay using the half-life of that nuclide. We can use that to figure out how old some really old crap is. And so we looked at two specific examples. One we used for once living organisms, this carbon-14 radio dating, and the other we can use for certain types of minerals, this uranium-lead dating. Cool. All right, we got one more topic to discuss here. In nuclear chemistry, and that is nuclear power. All right, what's the first thing that comes to your head when you hear nuclear? Chernobyl, right? So bombs, all this maybe not so great stuff. All right, so that's because nuclear was discovered sort of in the early 1900s, and it was at the time something that was both very scary and very promising. Early scientists quickly realized both its potential to help and hurt humanity. All right, so specifically talking about generating power using nuclear, there's some pros. All right, so first of all, the fuel has a high energy density, which is a fancy way of saying a little goes a long way. And we're going to kind of see math-wise here, but in terms of like gram of fuel, it's just absurd how much more energy is created through a nuclear reaction than through a standard chemical reaction. It's also very reliable, meaning that its output is incredibly consistent. That's a big problem with like solar and wind, is this variable output, so you have to have a way to store it. Nuclear, you can get this very consistent 120 volt output constantly. It can be profitable in the long run, which is always good because nobody does anything for free. And then the big thing, the big pro of nuclear, especially in today's day and age, is it's a clean source of energy, meaning there's no carbon dioxide byproduct. All right, so then what's the cons? Well, the Chernobyls of it all, right? So there are a few, and they are pretty few and far between, but very high-profile accidents that have led to disastrous consequences. Chernobyl being one of them, more recently Fukushima. It's also not cheap to get a nuclear power plant up and running, so high investment costs. You got to have somebody willing to front a huge amount of money and not get any return on it for quite a while. And then the last one, exactly, is the waste generated. Right? So the waste that's generated is radioactive and will remain radioactive on the scale of thousands of years, which means you got to figure out something to do with it. Which most of the time means bury it in these huge concrete crates in the desert somewhere and just don't touch it forever, right? Just put it somewhere where nobody's going to interact with it for the rest of their lives. That's the goal. You know, it's sort of unfortunate because nuclear is really a fantastic source of clean energy. You know, it's not really talked about anymore because of the high-profile accident. Fukushima happened like 2011. If you think Obama got elected in like 2008, and so climate change, a big push, a lot of discuss of nuclear energy in the future, and then all of a sudden there was a huge meltdown of this plant in Japan, and everybody's like, okay, JK, We'll try a different route, all right? And it really kind of put a stop to any and all investment. Our country currently is maybe 20-25% nuclear. There are other countries that made much bigger investments. France, I think, is on the order of 70% nuclear. And yes, a lot of these times we don't really have very many incidents. Chernobyl is one example of like human incompetence, or rather, I don't remember what exactly they did wrong, but somebody did something wrong somewhere. Fukushima was a much more like sudden natural disaster that occurred. There was an earthquake that triggered a huge tsunami. Japan is a bunch of islands. Yeah, you had a massive wave crash in and just knock that plant out of commission. So anyways, that whole thing just kind of turned people off to nuclear power. But I mean, hey, if we got one up and running in the desert somewhere, that'd be great, right? Because it is a great clean source of energy. So we're kind of sleeping on it, but it is what it is. Okay. There's kind of two main paths that we can take to generate nuclear power. The one is the one that we actually use, and that is what's called fission. Fission happens when a large nuclei breaks into smaller nuclei. And of course, the whole reason we can get power from it is because it releases a ton of energy. This is actually what we use. All right, so when we're talking about nuclear power plants, we are talking about fission reactions that occur. All right, so how exactly does this work? So this uses another uranium isotope, uranium-235. And what they do is they take that uranium-235 and they chuck a neutron at it, right? They collide it with a neutron. So neutron, in terms of our nuclear equations, has a mass number of 1 and an atomic number of 0. Well, this is going to cause that nuclide there to be unstable, and it's going to break apart into these smaller pieces. It breaks apart into barium-140. Krypton-93. And a whole bunch of neutrons. And I want you all to take a second and balance this nuclear equation here and tell me how many neutrons are produced. All right, how many neutrons? I'm going to need 3 of them. Cool. So how does this fission reaction produce energy? All right, so I'm going to tell you essentially one of the things that happened. First of all, so much advancement in chemistry and physics happened during this same period in the early 1900s when they had these world wars going on, because all of a sudden these governments started chucking money at science like they've never done before, right? So we really see like a big acceleration in scientific advancement during this time period, nuclear being one of them, okay? So one of the tools that we got was this really accurate way of measuring masses of individual atoms. All right, so we're going to go and we're going to measure these masses here. I'm going to tell you that uranium-235 here has a mass of 235.04392 AMU. A neutron, a mass of 1.00866 AMU. All right, barium's 139, 910581. Krypton's 92.931130. And our neutrons, we got 3 of them. But again, that's that same mass we said before of 1.00866. All right, so based on everything that we've learned up until now in chemistry, what would you assume would happen to the mass of our reactants compared to our products, our total mass here? Should be conserved, right? Based on everything we've learned up until this point. So let's sum it all up and figure this out here. All right, I'll tell you what. Y'all do the left-hand side, I'll do the right-hand side. All right, what do we get for the left-hand side? 236.05258. And if we add it up on the right-hand side, you can trust me on this one, we get 235.867691. So did we get the same number here? No, all right? And this was this discovery that was like, oh shit, this is crazy here. They realized that a mass of an atom is not simply the mass of the sum of the number of protons and sum of the number of neutrons. You always lose mass, all right? And this is what they call a mass deficit. This is why splitting an atom, which is what we just did here, we split this uranium, yields so much energy, is because of the mass deficit. Because these smaller parts combined together actually have less mass than the big thing that you started out with. All right, the mass deficit, this is our mass lost in our nuclear reaction. All right, but wait a second. I said that this produces energy here. So how does mass loss correspond to energy? What is Einstein's famous equation here? E equals mc squared. The c is the speed of light, right? So what are the only two variables in here? It tells you how much energy you get based on the amount of mass lost. And so when they discovered this mass deficit, they were like, oh my goodness, this mass loss can be used to produce huge amounts of energy, for good or for bad. All right, so for this particular reaction, let's figure out just how much energy we're going to get here using our equation. Let's first figure out our mass loss here, our mass deficit, the m in this equation. All right, we're going to simply subtract our two masses. I was sloppy about my units here, but these are in AMU, atomic mass units. All right, we're going to have to do a bunch of unit conversions in this equation here. M, or rather C, is in units of meters per second. And energy, a joule, is defined as a kilogram meter squared second squared. So we're going to have to convert our AMUs into kilograms before we can plug it into our equation here. All right, if we look on our constants page, we have this conversion that we can use from AMU to grams, and then we can get from grams to kilograms. All right, that conversion factor is that 1 AMU is this 1.6022. No, sorry, I was looking in the wrong place. 1.6605 times 10 to the negative 24 grams. All right, and then we need to get to kilograms here, so I'm going to use the fact that there are 1,000 grams in 1 kilogram. Now I'm going to multiply by my speed of light, also on my constants page. 2.9979 times 10 to the 8 meters per second. But I got to square that. All right, so punch that into my calculator. I'm just going to do 2 sig figs here. 2.76 times 10 to the negative 11. My units would be kilograms times meters squared divided by seconds squared, or joules. Does this seem like a big, scary number? No. All right. Until you realize that this is how much energy is released when a single uranium particle undergoes this fission reaction. And we're not used to talking about things in terms of individual particles. We're used to talking about things in terms of moles of particles, right? In particular, when we're reporting energy released in thermal energy, our delta H values, we like what? Units. Kilojoules per mole, all right? So let's convert this to something that we can be more familiar with, a kilojoule per mole. We're going to multiply this first by Avogadro's number. All right, this is how many joules there are when one atom undergoes this fission reaction. So we're going to use the fact that there are 6.0221 times 10 to the 23 atoms in 1 mole. All right, and then we're going to do our joule to kilojoule conversion just to make it look good. There are 1,000 joules in 1 kilojoule. And now we get E equal to 1.66 times 10 to the 10 kilojoules per mole. That is a lot. All right, to put this in perspective, the most exothermic reaction, what we use to power our cars and all that jazz with, right? This energy that we get from making and breaking chemical bonds is around 1,000 kilojoules per mole. Right? That's kind of the max amount of thermal energy that you can get in a chemical reaction. That's a good ceiling to sort of have in your mind in terms of what's reasonable for a delta H value. The energy that we get released from a fission reaction is what, 7 orders of magnitude greater than that? All right, so these fission reactions produce a huge amount of energy compared to reactions that just, compared to chemical reactions, which are about making and breaking chemical bonds. All right, so the bottom line here, we get a huge amount of energy. And again, where did that energy come from? It's all about that mass deficit. Cool. So, one other thing to note here is that this reaction requires you to combine a uranium atom with a neutron, but then notice that you're producing 3 neutrons as your product. Well, what are those high energy neutrons being shot out going to do? They're going to go and hit other uranium-235s. This produces what they call a nuclear chain reaction. The neutrons produced will collide with other uranium-235 atoms, and it'll just keep going and going and going and going, right? So once you kick off this reaction, it kind of just keeps going and going and going, which is exactly what they had in mind when they created the nuclear bomb, right? Let's kick this process off, and it's just going to chain reaction out, producing huge amounts of energy at every step. What's up?
So is that why it's so dangerous to have anything go wrong in like nuclear?
Totally, right? So they have ways of controlling this, what they call it, and this, we don't have to know this, but fun fact, they have these ways of controlling this called neutron absorbers, these little rods that they stick in there. And they make it so not too much chain reaction is happening at any given time. Exactly what went wrong in like Fukushima was that system broke down, and all of a sudden this thing just went and kept going and going and going. It got so hot that it melted through all of this safety precautions that they had in place. Just had this big blob of nuclear metal or nuclear reaction just kind of melt out the bottom of this nuclear power plant, and unfortunately into the ocean. Anyways, better not to think about that stuff. Cool. All right, one more here. We're going to run over here so I can get this one thing out of the way, and then we'll take a little bit of a longer break before we start our lab. There's one more type of nuclear reaction that we wish that we could do in order to create power, because it actually creates even more than the other type, and that's what's called nuclear fusion. This is where you combine small nuclei to create larger nuclei. Again, this releases a ton of power. Or more specifically, energy. All right, these fusion reactions happen all the time in our galaxy, but specifically where they find them, these are the reactions powering stars. So why is our sun just constantly bombarding energy at us? It's basically a core of fusion reaction that's taking place. It's made up of really tiny elements, hydrogen and helium, and it's smacking them together, creating larger elements. And that's what all this energy that's being released is coming from. It's also why they have a finite lifespan, right? Stars eventually die out because they use up all that fuel. They use up all the amount of energy that they got in there. Unfortunately, we know that this exists, and we can do it here on Earth, but it requires very high temperatures and pressures. And unfortunately, how do you get something to a very high temperature? You have to put in a lot of energy. They have not figured out a way to do this that would be cost effective or energy efficient. In order to get this to occur, you end up having to put up more energy than you get back out of it, making it a net loser in the long run, right? So we can do it in a lab, but you end up spending way more money trying to get it to actually occur than you get back out energy-wise. So that's why, practically speaking, this has been an elusive sort of source of energy in our nuclear power. All right, so one just sort of sample reaction here to show. This is one of the ones they were kind of hoping that they could get to work. If we take 2 hydrogen atoms and 2 neutrons, all right, I'm going to tell you that this makes just one product over here, and I want you to tell me what that product is based on balancing our nuclear equations. All right, this would create a helium-4 nuclide. So why does this produce so much energy? Well, again, we can sort of skip ahead, fast forward to the details here. If we sum up everything on our reactant side, we would get a mass of 4.03298 AMU, and a helium-4 atom has a mass of 4.00260 AMU. So what happened to our mass? Did it go up or down? Went down. So remember, that's what we call a mass deficit. And that mass loss, where did it go? Got converted to energy. With that huge scaling factor of c squared. So again, we could use Einstein's equation here to figure out exactly how much energy is produced in this fusion process. All right. Cool. So in terms of our nuclear power reactions, we got 2 different categories. We have our fission reactions, where we break something up into these 2 smaller nuclei. That releases a ton of energy. Well, how does that release energy? Because we have a mass deficit from our reactant side to our product side. There's mass lost in that reaction. And according to Einstein's equation here, we can figure out exactly how much energy is produced. We also do the exact opposite. We can take these teeny tiny things and we can, we can take these teeny tiny things and we can combine them together. All right, those are the reactions that are powering our stars. And that also creates this same mass deficit where that mass then gets converted into energy. We could use Einstein's equation here to calculate exactly how much. Okay, so importantly, you can't just do this forever. All right, there's kind of a limit here. This is just sort of fun facts. You don't have to get too hung up about this. There are just certain nuclei that are more stable than others. All right, so if we have a very large nuclei, it will undergo a fission reaction. If we have a very small nuclei, it can undergo fusion reactions, but you sort of reach a point on your periodic table where these elements won't undergo any such nuclear reaction. All right, these tend to peak around iron. Is the most stable nuclide. You can't do any reaction with an iron nuclide that will have it produce energy. You're always going to have this net loser going on. So little things will combine together to make iron. Big things will fall apart to make iron. All right? So fun fact, iron is the most abundant element on this planet. Most of it's sitting in the very core of our planet. And that's the same actually for most rocky planets, is that there's abundance of iron in there. That's because all of these fusion reactions happening in stars, as well as fission reactions happening when we have these very big elements, they all trend towards the middle of the periodic table here. Yeah. But anyway, so only little things we can do fusion reactions with, only really big things we can do fission reactions with. That's the punchline of this graph. What's up?
I was just gonna say, I remember reading something about like stars, how when they become like red dwarfs and then finally like die out, their core of like iron and such,
Yeah.
it just becomes so heavy that it can't turn into, that's what turns into a black hole, right?
I don't know nothing about none of that. I'm not even gonna lie, even a little bit. But I do know that the stopping point is iron from a like chemistry standpoint because it's the most stable of all the nuclei. You can't do anything with it. It's not gonna fall apart into little stuff. You can't combine it with other stuff to make bigger stuff. So it's kind of the end point of all of that. But I don't know anything about space. I'm not gonna lie.
I remember that the iron like core becomes so compacted that the weight of it collapses in on itself in one chain of like how stars can go, and that's what turns into a black hole sometimes.
Yeah, I mean that
Our
totally.
star is not going to turn into a black hole.
No, you have to be a certain type of star in order to do it. Yeah. No, I know enough to know that I know like nothing about that sort of stuff, but it is really interesting and it's all well documented. I mean, it all is a lot of, again, nuclear chemistry. From a chemist's standpoint, it happens in the smallest little sector of chemistry. It's a huge part of astronomy and physics as well, right? Generating power and stuff. So,
I know just enough to give a little fun fact.
yeah, awesome. That's what you need, the party tricks of it all. Cool. All right, so we're going to close it out there. We ran a little bit over. That's okay because today's experience